Let's take a look at an example problem for an RC differentiator. So they ask us in this problem to draw the output for the differentiator as shown. So I'm going to use the expanded views here. So the first thing we need to do is calculate what the time constant is going to be for this circuit. 120 picofarad, 15 k ohm resistor. We've got a 5-volt input square wave at a pulse width of 10 microseconds. So tau is equal to RC. So in this case, 15 k ohms, 120 picofarads gives us 1.8 microseconds of one time constant. So we know that to reach the full charge across the capacitor, we have to be greater than or equal to the 5 time constants. So if we look at the output is going to look like this. We end up with a 5-volt peak to start with. We end up with a 10 microsecond output for our output across the resistor. On the rising edge, the resistor jumps to 5 volts, then decreases exponentially to 0 by the end of the pulse. When the falling edge, the resistor then jumps to minus 5 volts, then goes back to 0 exponentially. So if you look at the example then in your text, that's just exactly what that is. In this case, the pulse width is greater than 5 time constants, so the capacitor reaches full charge before the end of the pulse. On the rising edge, the resistor voltage jumps to 5 volts, then decreases exponentially to 0 by the end of the pulse. On the falling edge, the resistor jumps to minus 5 volts and then back to 0 exponentially. The resistor voltage then, of course, is the output, and its shape looks like this, as we've seen. Okay, the second one here says determine the output voltage waveform for the RC differentiator with the rheostat set so that the total resistance of R1 and R2 is 10 k ohms. Okay, so if we take a look at this, if we calculate the time constant, the resistance total then equals 2K times 1 microfarad. 2 milliseconds is our time constant. So we need to use the exponential relationship. V out is equal to V initial times the exponential of minus T over RC, or T over tau. Excuse me. 25 then volts is our initial, 25 volts. E to the minus 5 milliseconds divided by 2 milliseconds gives us a value of 2.05 as V out. So we can see here then the depiction then of the drawing of the waveform as we calculate the output. So first we calculate the constant. We did that. On the rising edge, the resistor voltage immediately jumps to 25 volts. Because the pulse width is 5 milliseconds, the capacitor charges for 2.5 time constants and therefore does not reach its full charge. You must use the formula then for decreasing exponentials in order to calculate what the voltage output decreases by the end of the pulse. So there is our exponential value. Again, V out is equal to V initial times E to the minus T over tau, or minus T over RC, and we get that 2.05 volts. So where V initial was 25 volts and the pulse width was 5 milliseconds, this calculation gives us the resistor voltage at the end of 5 milliseconds pulse width interval. On the falling edge, the resistor voltage immediately jumps from positive 2.05 volts down to minus 22.95 volts, a 25 volt transition. The resulting waveform of the output then is drawn. So we can see that here in this in this example here, the drawing. So the RC differentiator with a single pulse.